For this method, you would start with, let's say, a search space, and you put there, for the beginning, randomly, n points, where n is at least the number of dimensions plus 1. Well, a good choice mostly is 2 times the number of dimensions, but for the method to work you need at least more than the number of dimensions. So let's say I start with 4 points at the moment. So randomly I find 4 points. So this is the beginning. Now all those points could be somehow evaluated and sorted according to error function. So there is one of them which is best and one of them which is the worst one. Surprisingly, we are not going to work with the best one, but we will work with the worst one. So let us evaluate them, and let's say this is the worst one. Now we calculate the average of all other points, kind of center between them. So if I can take an average of the 3 remaining points, let's say this average would be somewhere here. And what we will do now is that we will move the worst point, the point with the greatest value of error function, and we will reflect it around this center. But we will not only reflect it, but we will reflect it so that it falls not, so it moves along this line, but it moves so that the distance is not only reflected but also increased with a factor 1.4. So in fact it falls somewhere here. And now there are 2 possibilities. This new point could be better than the old one. If it is better, we will forget this and replace in the set of points that point by this new point. If it's not better, that is, if its error function is less than, is not less than this old one, or if it falls out of the margins so that it is an unacceptable value, we will move it 1/2 to the center. So if it's not that case, we will move it here. And again test, is it within margins and is it better than the old one? If yes, we will replace this point by this point. If not, we will move it 1/2 to the center. And we will repeat that as far as we get a better solution than the worst point, or we get to the center. Well, what means we get to the center depends on your programming. So you select a constant, and if this falls more or less to the center, you give up. There is no possibility to reflect the worst point. This is a rare case, but even possible. And then you try to reflect the second worst point. Now this somehow works, and due to the over-reflecting, this method somehow is capable of running downhill. So it is capable of somehow tracing the gradient. For example, if I use this as the error function, so the worst point would reflect here, then the worst point would reflect somewhere here, then the worst point, which would be this, would reflect somewhere here, and as you can see, the the distance between points when running downhill is increasing, so that the set of points is running faster and faster if there is a clear gradient, a clear downhill direction. On the other hand, if you have, for example, a hill, I will now draw only 2D, we have a hill and the points are sitting around it, then this is a problem for the method, because the center falls to a location which is much worse than the other points. So the point will very easily handle the situation where those points are located around the optimum, because then it is in the center and it moves fastly down. But if somehow happens that we have a hill and the points will sit around, that would be a problem. To overcome this situation, we have an extra method, and that is that if it is not possible to reflect the point, not the worst, not the second worst, not the third worst, and then we replace the worst point by a random point, a randomly selected point, and start the whole again. This method is very simple. In fact, we have a few rules. Select the worst one, try to reflect it. If the reflected point is better, accept it. If not, is not better, move it to the center 1/2 way and repeat. And there is the second rule: if you fall into the center and the center is not better than the worst point, try to reflect the second worst. And the third rule: if not good enough, increase the number of points by another randomly selected point. The method has been published in Computer Journal by Michael Box in 1963. What I have presented here is slightly modified, but anyway, this method proves to be quite an efficient one. So this was one of the methods I like most and I use for optimization of microwave and radio frequency circuits as the first choice. Still, please remember, for any method that is possibly convergent, there is a problem for which this method is optimal. But to seek for an optimal method is very uneasy, because mathematicians have proved the previous rule, but they are not able to tell you which method is best for a given problem. So each of researchers has one, let's say, favorite method. This is mine. And then if this does not work, we have to switch to other methods like gradient and so on. Now I would like to finish this part, because this is one method, classical optimization, published 1963, and I will now switch to, let's say, modern optimization methods. What they mostly declare to be, they are called global. Most of those methods are somehow inspired by the nature. Well, that is, you would hear that like ant colony or genetic methods or evolutionary methods. Well, it is clearly seen that the mathematician or the scientist who has been developing those optimization methods have seen a little bit of biology, but not much. So they only resemble biology somehow. The important point we have to learn is that those methods, as the generation has changed, somehow have a little bit switched the paradigm. So in classical optimization, most of the optimization tasks were aimed at minimizing the error function. Well, in modern optimization methods, there are two things that are completely different. First, the function is not called error, but mostly is called fitness. Well, it is a fitness function, so the more fit is the solution, the better it is. So since then, we are aiming at maximizing function. Fortunately, if you have the error function and you want to create a fitness function, you can easily do that, for example, as fitness function is equal 1 minus error function. And you have a function which for the same problem has a maximum on the point where the previous error function had a minimum. So it's easily converted. Now, it's important to show that those methods work possibly with bigger computer load, and they are called global because they are at least aimed not to be sensitive to global or local minimums and to find a global minimum on large data sets or in large search spaces. Well, although there has been done a lot of work to achieve that, I would like to suggest to you that anyway, before you start optimization, you try to find quite a good estimate of the result. Because despite of the fact those methods are declared to be global, they still do not find global optimums at each case. So that's it. Now please, I would like to switch to the first of those methods that are, let's say, global optimum finding. And to do that, I will start with something which is called genetic optimization. Now, what a genetic optimization means in fact. Genetic optimization has been pioneered at the end of last century or millennium, and it has at the beginning more or less this idea. Well, if you represent any information within a computer, finally you might think those are real numbers, those are somehow represented graphs or connections or compositions of something. At the end, you always finish with a sequence of bits. So what you have in today's computers is a string or a field of bits, zeros and ones. Yes, and possibly some part of that sequence of bits represents a real number. Other part could represent a connection from somewhere to somewhere in a circuit or the geometry. But anyway, it is a set of bits. And now we will look on this set of bits with the different eyes. Somebody has seen some work from Darwin or some genetic research, and instead of bits, we would call that alleles. That's something you have in a chromosome. So alleles. And instead of a string of bits, you would see a genome and genes. So So far we have been only naming the same situation, a set of bits in a computer with different names. Now I will present to you a simple genetic algorithm where we can see the most important parts of it. And then, once I will present this, I will a little bit comment on possible blends or variations in the algorithm. So first, you need to have several variants of that. The scientist has possibly seen a piece of nature where there are many, for example, kangaroos or many deer in a herd. And what this is represented by, you first generate a number of kangaroos, deer, or electric circuits. So you randomly start with a number of sequences of genes and alleles. Let's say you get 50 of those, and you have just a randomly selected bits. So you make something like a population. The population in this case means a set of zeros and ones. And then for each of those you calculate the fitness function. Now you can start with selection. So that scientist has possibly read something from Darwin, and that selection should be done based on fitness function. But this is not the whole. You have to somehow create offspring of two, let's say, of a father and a mother, and you have somehow to select them. So you have, let's say, 50 representations of an electric circuits that are bits, so portions of zeros and ones, and you have to somehow generate more circuits or next generation of those. And what you do is, first you have to somehow select the two strings that you will somehow combine to get offspring. The first method of selection is random. So you randomly, from the pool of, let's say, 60 initial strings, you randomly select two. Possibly random selection is not the best idea, but we will start with it. So we randomly select two of those, and we have to somehow produce offspring out of them. And this is one of the important tricks used here, which is called cut and splice. In fact, this is the main method used in all genetic algorithms. So let's say we have two genetic information represented by zeros and ones, first and second. To be able to make a clear example, I would somehow, so let's say that this is 1, 1, 0, 1, 0, 0, 1, 0, 1, 1, and the second would be 0, 1, 1, 0, 0, 0, 0, 1, 1, 1. Now the cut and splice method, in fact, has two steps. In first step, you randomly select a position. So randomly you, for example, select this position. Now you make a cut of both chromosomes, and you connect the first part of the first chromosome with the second part of the second chromosome and the first part of the second chromosome with the first part. So, for example, what you form now is this and this. So let us write the offspring in a detailed way. So we will have two children. So the first child would have the first part of the first chromosome and the second part of the second chromosome. Let's write it down. 1, 1, 1, sorry, 0, 1. And now from the second part, 0, 0, 0, 1, 1, 1. And we can put down the other child. 0, 1, 1, 0, 0, 0, 1, 0, 1, 1. So we have produced two children that somehow inherit from their parents. There is a big portion of randomness in this. But anyway, somehow this works. And we, of course, do this many times so that we create a big population. So we have, in this route, we have initialization, then we had selection, which selects parents. We have cut and splice, that generates new offspring. And to more mimic the nature, there is another operation which has a random effect in it, another random effect. Some portion of that offspring is randomly modified, which is called mutation. So let's say from 50 randomly generated